oh, okay. You guys ready to learn Taylor's theorem, where you're going to learn about the Lagrange form of the error? Ooh, Ipok's here, though. Everyone's here today. How exciting. This will be probably the most difficult thing we'll ever learn this year. I'll do my best to teach it to you in a way that's easy to understand, but this is like so difficult that it's kind of hard for me to teach it well. But here goes, okay? The Lagrange form of the error, Taylor's theorem. First of all, when you get an approximation of something, it's convenient to know how accurate that approximation is. For example, when my wife says dinner will be ready in 30 minutes, I know it's going to be 30 minutes, plus or minus 5 minutes. I know I can count on her approximation of when dinner is going to be ready to be pretty solid. Whereas when I ask my 8-year-old daughter, when are you getting off of the computer? And she tells me I'll get off in an hour, well, I know it could be as much as 8 hours. I mean, who can say, She's 8 years old. And so when someone gives an approximation, it's useful to know how accurate that approximation is. And it's the same thing with Taylor polynomials, and don't write this down, this is just all intro. When I have e to the x equaling 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot, 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 that's the Maclaurin polynomial expansion for e to the x. And I decide, well, you know what? I'm not going to add up an infinite number of terms. I'm just going to use the second order approximation. Okay? So, oops, I'm so sorry. Again, don't write this down. I'm going to use this second order approximation to approximate e to the x. And at this point, it's going to be, okay, well, I'd like to know how accurate this approximation is. I know it's not going to be on the button except at x equals 0, of course, because that's how these approximations are constructed, where the functional value, the first derivative, second derivative, and all the other subsequent derivatives are identically correct at the center at which you're doing your expansion. But beyond the center, I don't know how accurate this approximation is going to be. How close to this guy is this guy going to be? And so Taylor's theorem tells me that. Taylor's theorem says, I'm going to tell you about how accurate your approximation is. Now, in the days before computers, because nowadays this is a weird way for you guys to think, because you go, why do I need this approximation? I'll just plug that into my calculator. I'll plug this into my computer. But it's kind of like we're hearkening back to a day and age where we didn't have computers and calculators, a day and age where people are doing their math with just pencil and paper, where it's infinitely easier to deal with this than to deal with that. People couldn't deal with this at all, whereas people could deal with this easily. So it's kind of weird that we're valuing polynomials way, way more than crazy weird functions when we live in a day and age when you can just plug crazy weird functions into your calculator and it works out just fine. So you're going to have to bear with me and somehow assign this incredible importance to being able to get polynomial approximations of weird functions. But that being said, our goal is to say, okay, how accurate is it? Is it going to be plus or minus 5 minutes like my wife's dinner, or is it going to be plus or minus 7 hours like my daughter being on the computer? You see what I mean? So that's it. That's what today is all about. And now it's time for me to teach it to you. Teach it. And I'm going to have to refer to my notes. Okay. Hold just a second. Or let me do one more intro-y thing. I'm so sorry. I was going to skip this, but I'm not going to. Okay. Here, more intro.
Should we write this down?
No, don't write this down. This is still intro. This is just to get your heads in the right place. Let's talk about the sine of x. Okay, the sine of x. When we do the the Maclaurin approximation of sine of x. I don't know if you remember, but all of the when I'm plugging in 0, the functional value is 0. Like the sine of 0 is 0. So the functional value is 0, the second derivative was 0, the fourth derivative 0, the sixth derivative is 0. I don't know if you remember actually constructing these, but I'll show that to you later. But I just want you to see that the sine of x ends up being this. This is the Taylor expansion of the sine of x, okay? It's just all the odd terms. And that happens because when we do this thing, you know, f of x equals sine of x, f prime of x equals cosine of x, etc. When we do that thing, it turns out that all the even, you know, derivatives end up being 0 when I stick 0 in for them. Alrighty, so now I'm going to get the sine of pi over 6. The sine of pi over 6, well, wait, oh my god. No, I feel so stupid, I'm fumbling and bumbling now. Okay, so let's say I want my sine of x, I just want the third order approximation. Okay, so that's it. I'm going to say sine of x is approximately equal to this. Okay, how good of an approximation is this? Alrighty, well, let's try a number. How about the sine of pi over 6? The sine of pi over 6 is approximately equal to pi over 6 minus pi over 6 to the third power over 3 factorial, okay? The sine of pi over 6 is 0.5. And pi over 6 minus pi over 6 to the third power over 3 factorial is 0.49967. Okay, so we go, okay, for pi over 6, this third order approximation is an amazingly good approximation, okay? But let's try it for other ones. How about pi over 2? Sine of pi over 2 is going to be approximately equal to pi over 2 minus pi over 2 to the third power over 3 factorial. Well, the sine of pi over 2 is 1, and this stuff here is 0.925. Well, that's not as good an approximation. Now I'm 8% off. You see? Well, how good of an approximation for the sine of pi? Hey, sine of pi is approximately equal to pi minus pi to the third power over 3 factorial. Well, the sine of pi is 0. And then pi minus pi to the third, I don't happen to have that done here, so I'm going to do that right now. Just 1 second. So I got pi minus pi to the third power divided by 6. And that gets me negative 2.03. Was that a good approximation? No, I think we can all agree that it's starting to suck, you know? Well, I don't want to have to do this a bunch of times for a bunch of numbers. I want to just have one equation that I can plug into that tells me how good or bad my approximation is. And that's what Taylor's theorem does. I want to say it again. Rather than me doing this multiple times for every number I'd care to plug in, I'd like to have just one equation that does it for me. And that's what Taylor's theorem is. Okay, thus ends my intro. And now it's time to learn it. Here we go. So please write this down, okay? Taylor's theorem. There exists a z such that z is between c and x, such that f of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus dot dot dot. Oh, I ran out of room. Oh, that was dumb. Sorry, kids. Such that f of x equals f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus dot 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 plus the nth term, the nth derivative evaluated at c over n factorial times x minus c to the n power plus r sub n of x, where r sub n of x equals the n plus 1th derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1 power. Let me wait till you guys get this written down, and then I need to interpret this for you. Here's what's going on. Okay, using Taylor and Maclaurin polynomials, usually, you can get a weird function to be exactly equal to an infinite power series, a power series with an infinite number of terms. And it will be totally the same thing. This will be the very same as this, but only for the interval of convergence. Only for the, like we did with the geometric power series, only for certain values of x. Is this identically the same as this? For the other powers of x, you stick those powers in, you get a number, you stick those, or rather you stick those x values, you get a number here, you stick those x values outside the interval of convergence into here and you get infinity. Okay, but for the interval of convergence, this infinite power series will be identically the same as this. But quite often you don't want to use an infinite power series. You want to use an approximation that has only a finite number of terms. You see? And so if you're going to use an approximation with a finite number of terms, going up to whatever degree you'd like to go up to, in this situation, I went up to degree 3. Here, you're going up to degree n, okay? But if you're going to approximate a function with a finite number of terms, then you're going to be off. You're going to have an error. You saw that happening here, where for pi over 6, the error was 0.0003. For pi over 2, the error was 0.075. For sine of pi, the error was 2, you know? But whatever happens, if you're going to approximate a function with a finite number of terms in your polynomial, then you're going to have an error. And this guy here is the error. They call it the remainder. And so this is actually called the Lagrange form of the remainder. Okay, Lagrange, oops. I'm thinking of the ZZ Top song. Lagrange form of the remainder. Okay, they call it the remainder, but really it's the error. It's how much off you are. It's how much you have to add or subtract to these guys so that the right side of the equation is identical to the left side of the equation. So for example, the remainder here was 0.075. The left side exactly equals the right side. You know, as long as you add 0.075 to the right side, then you're good, you know? But this remainder is a function of x. The remainder, how much off you are when you approximate some weird function with a finite number of polynomial terms, how much off you are depends on the x that you're plugging in. You know, it depends on whether you're plugging in pi over 6, pi over 2, or pi. You get a different remainder each time. You're off by a different amount each time. So we would like to have a formula that tells you how much you're off by, and this is that formula. This tells you how much you're off by, where it's a function of x. You know, if for that here, if I want to know how much I'm going to be off when I plug in pi over 2, then this is going to be r sub n of pi over 2, or really r sub 3 of pi over 2. And then my x is pi over 2. So that's what you're getting, a formula for how much you're off by. Now, here comes the weird part. You don't really know what this is because you don't know what z is. All you know is that z lies somewhere between the center of my approximation and the point I'm plugging in. If the point I'm plugging in is less than the center of the approximation, then z lies between them. Or if the point is that you're plugging in is greater than the center, like what happened on every one of those, then it's going to look like this. But either way, you can never know what z is. All you know is that a z exists somewhere on this interval, so that so that you can get the exact value of your remainder. So if I can actually put this in words, the problem is you can't know what z is. You just know the bounds of z. Z is somewhere between c and x. So a lot of times when we do this remainder stuff, rather than finding specifically what z is, because you can't do it, we end up caring more about what the maximum value of this guy is. That is, we end up caring more what the maximum of the remainder is, which is going to be the maximum of this n plus 1 derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1. Okay, well, hey guys, it is now time for us to do like about 6 examples, and hopefully by the end of doing these 6 examples, you'll like have a sense of what's going on. Because right now, you should be clueless. If anyone's not clueless, then you're an alien, and that's okay. Okay, here we go. Example number 1. Find maximum possible error in approximating sine of 0.5 by using the sine of x is approximately equal to x minus x to the 3rd over 3 factorial. Please write that down. Okay. I need to construct this. I need to construct this, or actually I'm going to be constructing that. So I need to know x, I need to know c, I need to know the maximum value of this guy, and I need to know n. Okay? So those are the things I need to know. I need to know x, c, n, and the maximum value of the n plus 1th derivative evaluated at z, the maximum value of that. Once I get all those, I get to plug into that equation and get my answer. And really, it's that simple. So you tell me, what's my x equal to? What am I plugging in?
0.5.
Good, 0.5. You guys got that. Great. What's my c equal? What is my approximation centered at? 0. What if the approximation was centered at 1? Then what would these terms look like?
X minus 1.
Yeah, they look like x minus 1s. So you can always tell where you're centered at by just looking at the x terms. If this was x minus pi over 4 and x minus pi over 4 quantity to the third power, then it would be centered at pi over 4. Okay, great. Let's get our next guy. N. What power approximation is this? You'd think,
4.
yeah, how'd you know it was fourth power?
Because 4 is a 0, so
You guys okay with that? It's not fifth power, because we don't have x to the fifth over 5 factorial. So it's not fifth degree, but it is fourth degree, because the fourth degree term is 0 x to the fourth. And that sort of thing happens when you're missing every other term. So I just figured I'd let that be the very first example I give you so you get used to the craziness of things. But yeah, this ends up being a fourth degree approximation. It's just the fourth degree term is 0. So my n is equal to 4. And now, next I'm going to ask myself, what's the maximum of the n plus 1th derivative evaluated at z? Well, because n is 4, I want the maximum of the 5th derivative evaluated at z, where z lies between 0 and 0.5. Well, let's consider the 5th derivative of the sine of x, okay? Right? F of x equals sine of x. F prime equals cosine of x. F double prime is negative sine of x. F triple prime is negative cosine of x. F quadruple prime is back to sine of x. And f, the 5th derivative, is cosine of x. But I tell you what, I don't want to hurt my brain too much. I mean, sight unseen, what's the maximum value of the cosine or sine of x always going to be? Yeah, 1. So in a situation like this, I'm not going to make my life too hard. Now, of course, it does end up being 1 because z lies between 0 and 0.5, and the cosine of 0 is 1. You see what I mean? So it ends up being 1. But I'd say almost always, if you're presented where your derivative is sine or cosine, just let it be 1. Let the maximum value be 1. But in this case, it actually is 1, you know? Because my z has to lie between, and I'll put this in parentheses, you know, my z has to lie between 0 and 0.5, and the maximum value of the 5th derivative evaluated at 0 is 1, you know, or the value of the 5th derivative is 1. Okay, go ahead. Okay. So now that I know all this stuff, I get to answer the question, you know. Number 2, plug in. Okay, so the maximum value of the error in the 4th degree approximation evaluated at 0.5 is going to be 1. You know, the maximum value of that guy, which is 1, over 5 factorial. Are you okay? Because it's the error in the 4th degree term. So it's 5 factorial. And then x minus c, so it'll be 0.5 minus 0 to the 5th power. And this ends up being approximately 2.6 times 10 to the negative 4th. So that's telling me the maximum possible error. Now, it's kind of weird because we're living in the day of calculators. So tell me, instead of going through all this problem, how could I actually find the error in the approximation? Like, I can actually find what the error, what the difference between the sine of 0.5 and plugging 0.5 in here is, right?
Yeah.
Just plug it in,
Yeah.
okay? You know, so it's weird living in the day of calculators. The sine of 0.5 is approximately, and I know I must have it written here somewhere. Oh, please, Larry, you had to have written it down. Oh, oh, wait, what? I don't have it written down here anywhere. How can that be? Well, whatever.
4.79.
Thank you. Let me make sure I'm in radians mode.
4.
Okay, yeah, so this is 0.4799426, and then 0.5 to the 0.5 minus 0.5 to the third power over 3 factorial is approximately equal to 0.5 minus 0.5 raised to the third power. I believe you, whoever said the answer, but I'm just going to punch it in because 9167. Okay, so the maximum possible error is 2.6 times 10 to the negative fourth, and that's about what I got here, right? The difference between these two guys is about 2.6 times 10 to the negative fourth. Okay, so you can get the actual error, just get the difference between the approximation and the true value. But this allows me to plug into the Taylor approximation and let her rip. Okay. Hey, I got to give you another one here. Here, just a second. Let's go ahead and do what I call in my page example 2A. Where's example 2A? Okay, here we go. All right. I'm going to have to erase this, which I hate to do. But what can you do? Okay. Here we go. Get maximum possible error in approximating e to the 1.6 power by the second order approximation. E to the x equals e plus e times x minus 1 plus e over 2 factorial times x minus 1 squared. Okay. So that's your problem. I want to remind you, you need to get xcn and then the maximum value of the, in this case, will be the third derivative, and then you plug it into the formula. So good luck. Okay, I'm going to intervene because you have a nice start on this. How many people got the values, the correct values of x, c, and n. Okay, yay. Now it's time for us to get the maximum value of the n plus 1th derivative evaluated at z. So you need the maximum value of the third derivative evaluated at z. Okay? Well, tell me, what does z lie between? What two numbers must z lie between? 1 and 0.6. Good. So z lies between 1 and 1.6. Okay? So you always, all you have to do is plug in the extremes. Here's my third derivative. Okay? The third derivative evaluated at 1 is e. The third derivative evaluated at 1.6 is e to the 1.6. So what's the maximum value of this guy going to be? E to the 1.6. It's that simple. Just plug in x and c, and whoever's biggest wins. Oops, e to the 1.6. Okay. So now that you got all those values, guess what? We're done. All I have to do now is plug into the remainder, the Lagrange form of the remainder. The remainder in the second order approximation evaluated at 1.6 is going to be the maximum value of the third derivative evaluated at z over 3 factorial times 1.6 minus 1 taken to the third power. That is, it'll be e to the 1.6 over 6 times 0.6 to the third power. And that ends up being, what did I get, 0.178?
Yeah.
Okay, 0.178. There it is. That's the maximum error between getting e to the 1.6 power and using that second order approximation. Oh, I forgot to put little curly equal signs here. Okay. So one way to express it would be this. E to the 1.6 power is approximately equal to e plus e times 0.6 plus e over 2 times 0.6 squared. So e to the 1.6 power is approximately equal to, I plug this in and I get 4.8385. Alrighty. That's what it is approximately. So because this is my maximum possible error, I can actually say e to the 1.6 power equals 4.8385 plus or minus 0.178. That is, I know it's going to be 4.8385, you know, somewhere within a neighborhood of 0.178 on either side, because that's my maximum possible error, is 0.178. And I gotta tell you, on tonight's homework, sometimes they're gonna give you a function and you're gonna have to figure out what the approximation is. I don't know if that happens or not, but I think that might. So you may have to be taking all the derivatives and using the Taylor's approximation that I taught you the other day. Okay. There's one more problem I need to show you, and then we're done. Here we go. Example number 4. Okay. What is the maximum value of x you can plug into the sine of x is approximately equal to x minus x to the third over 3 factorial, so that error is less than or equal to 0.001. Okay. So I hope you see that what we're doing now is I'm giving you this, and I'm asking for x, you know? You're not getting x, c, n, and the max. You're getting c, n, the maximum value, and the actual remainder, and I'm asking you to find x. So let's go for it. I'm asking you to find x, so that gets to be a question mark. But you tell me, what's my c?
0.
Good. And what's my n?
4.
Good. It's not 3, it's 4. Good. And then what's my maximum value of the fifth derivative evaluated at z? What's that going to be?
1.
No.
1.
Yeah, 1. It's still going to be 1, right? Remember where if f of x equals sine of x, then, you know, the fifth derivative is equal to cosine of x, and my z lies between 0 and whatever. We don't even know what the x is, but we know that cosine of 0 is 1. So the maximum value ends up being 1. So now I get to write out my Lagrange form of the error, the fourth order approximation at x, and I don't even know what it is, okay? That's gonna have to be less than or equal to the maximum value of the fifth derivative evaluated at z over n plus 1 factorial, and so n is 4. So I guess I'll write it out. I could have put a 5 there. And then x minus c to the 4 plus 1 power. Alrighty. So let's plug in. This guy is 1. This guy is 5 factorial. And this guy is x minus 0. So x to the 5th power. Alrighty. And we need this to be less than or equal to 0.001. So what comes next is I solve for x. So I'm going to have x to the 5th power has to be less than or equal to 0.001 times 5 factorial, which, if I'm not mistaken, is 120.
Yeah.
Good. And so x has to be less than or equal to the 5th root of, what is that, 1, 2, 3, so 0.120, which means x is less than or equal to, and do I have it here? Wait, no, I don't have it. Wait, I'm not really, Mr. Shana with his notes is not really helping himself. 0.12 raised to the 1/5 power. 0.654. So there it is, there's the answer. And you're going to get some problems on tonight's homework that ask you this, and you're just going to do it this way, you know? Plug into the Lagrange form of the error. So I can't plug in a value of x greater than 0.654, or I'm going to be off by more than 0.001. Well, kids? Any questions or issues? You'll notice I only gave you like 7 problems. So actually do them, think about it. Don't let this pass you by, or you won't, you'll never come back and learn it. Give it your best shot. Good luck. The Lagrange form of the error.
Right.